In this class, we're going to consider the rules that drive mathematical sequences. So remember that a sequence is an ordered list of numbers, but also those numbers have to obey some rule. And in this class, we want to figure out how to find those rules from the numbers. So let's say that we've got a sequence of numbers which starts with the first term of the sequence 2, and we'll keep it really simple. Let's say that these numbers are going up by 3 every time. So it goes 2, 5, 8, 11, and going up by 3, 14. So you're just adding 3 every time. So this would be an example of an arithmetic progression, arithmetic sequence, where we're just adding on 3, and we can keep doing that indefinitely. And that's fine, that's kind of easy, right? So we know how to keep generating the terms because we're just doing the same thing every time. So it's very tempting to say that is the rule, add 3 every time. That's kind of the rule in one way, but that kind of breaks down because let's say I wanted to know the 20th term. Do I really need to write out 20 numbers? Or worse than that, the 50th term, the 100th? By that point, definitely you can't be writing out all those numbers. So instead of generating a rule which takes us from one term to the next, which is what we're effectively talking about there, adding 3 every time to get from one to the next, we want to generate a rule instead that hits on the placement of the number in the sequence. So what we can do is start to assign, because remember a sequence has to be an ordered set of numbers, an ordered list of numbers. So these are not just randomly the numbers in the sequence, but they're also in the correct position. So we can say this is the first number, second, the third, the fourth, the fifth number, and that can start to get us kind of orientated in terms of where we are in the sequence. Now let's say that we did want to work out, for example, the 23rd number, instead of writing all the numbers out to 23, which wouldn't be terribly difficult in this case, but it would be time consuming and kind of boring and doesn't really give us much insight. Instead, we want to be able to go from the number 23 to this number. So in other words, we're trying to figure out a rule that doesn't go from here to here or here to here. We want the one that goes from here to here. How do I get from 2 to 5? How do I get from 3 to 8, 4 to 11? How do I get from 23 to its number? How do I get from 45, the 45th number in the sequence? How do I find that? That's what we're trying to figure out here. And it's actually not particularly difficult. What we do is we look at how much they're increasing by every time, and that gives us a little bit of insight. But just before we get to that, let's define each of these numbers as n. Okay, so we're going to call these are like our n numbers. They just represent the position that you're in the sequence. So number 1, number 2, number 3, 5th position, 23rd, 45th, etc. And we're just going to refer to these guys as u sub n. So these are the actual terms of the sequence dependent upon n. So we could write, for example, that let me switch back to black. So we could write, for example, that u sub 1, so the first term in the sequence is the number 2. U sub 5, u sub 2 equals 5, the second term in the sequence is 5, etc. U sub 3 equals 8. Okay, so you get the idea, that's just the notation for that. So we're trying to find basically a rule that links the n number to the un number in some kind of algebraic or formulaic way. And like I said earlier, the key is to notice that these are multiplying, these are going up in 3s. That 3 becomes our multiplier. So in other words, if you multiply the n number by 3, where does that leave you? What do you then need to do to get the number? So taking the first one, multiply that by 3 and you get 3. 1 times 3 is 3. We want 2, so we would need to subtract 1. So it seems like the rule might be multiply by 3 and subtract 1. Let's check that out on another number. Multiply by 3, 6, take away 1, 5. Multiply by 3, 15, take away 1, 14. So that tells us in general, our rule for this particular sequence is that un, like any number in the sequence, can be generated by taking 3 times n, whatever the n value is, and then subtracting 1. Okay, so just to test out on another one, let's take u4. So u4 should be 3 times 4, and then subtract 1. 3 times 4 is 12, take away 1, and you get 11. So that is validated. If we wanted to figure out this one here, so u23 23rd term in the sequence, we just apply the rule. So we do 3 times 23, and then we're going to subtract 1. So 3 times 23 is 689, take away 1, 68. So once you've got that general rule, it's very quick and easy to find the terms in the sequence. So that's basically how we go about that process. So that never really changes. It's fairly simple, unless you've got a very elaborate example of a sequence, which we're not going to look at here. You can get very complex sequences built on a much more complex sort of algebraic formula, but we're just kind of feeling our way into this topic. So this is perfectly fine at this point. Let's maybe take another example. So let's say that we start with the number 5, and let's just say that we're going to be adding, let me think of a good example. So let's just say that we're going to add 4 every time, just to keep it simple. So we'll go 5, 9, add in 4, 13, add in 4, 17, 21, etc. And that we just carry on. So just doing the same thing, we're going to assign our sort of position number to these. 1, 2, 3, 4, 5. You don't really need too many terms in a sequence to figure out the rule. I'm just going to say these are our n's, these are our u sub n's. Once you've done a few of these, you'll start probably dropping all of this information. It's just to help you keep track at first. So these are going up in 4. So that tells us our multiplier is going to be 4. So if we multiply 1 by 4, we get 4. We would need to add on 1 to get to 5. Does that rule, multiply by 4, add 1, work? Generally, so 2 times 4 is 8, plus 1 is 9. 4 times 4 is 16, plus 1 is 17. So figured out the rule. It's quite easy. So the general rule for this sequence would be un equals 4 times the n number, and then we're going to add on 1. And that will allow us to generate any term in the sequence just by plugging in the n number. So if you wanted to know the 100th term, rather than writing out 100 terms, which would take forever, you could just go 4 times 100 plus 1. 4 times 100 is 400. 401. Look how easy that was compared to writing out all those terms, which would be such a waste of time. So that's basically how you go about generating the rule for a sequence, and that is what the rule is. The rule doesn't connect each number to the previous number, like going this way. It connects the position number to the term in the sequence. That's what we're looking to do with these. So they're worth spending a bit of time on. They give you a good sense, these for sequences, and then you can move on in the future to more complex sequences and maybe even series, which is when we add up all the terms in the sequence. But getting this understanding now is a great place to start. From here, we're going to start looking in particular at arithmetic sequences and geometric sequences, which are 2 particular types. So that's the next place that we're going to stop off. So check those out in the next class.